All right, let's go ahead and begin. Welcome, everybody. Okay, so we're still in Chapter 4. We're going to be talking about some different types of fluid acceleration today. Just a reminder that your next homework assignment is due on Tuesday, and the problem set, of course, is on the handout that I gave you at the beginning of the semester, that course schedule. But for problem number 14, you need to give an explanation to support the conclusion that you come to. So it's not just the calculations, it's not just the answer, but just also a brief explanation for that one. Okay, so remember last time in class we talked about steady flow versus unsteady flow and uniform versus non-uniform flow. What was another way that we talked about flow being classified? Turbulent, and what's the other thing kind of on the other side of turbulent? Laminar, right. And what factor did you calculate to characterize whether flow is laminar or turbulent? What's the name of that equation? Reynolds number. Good. What are the units of Reynolds number? It's unitless. That's a trick question, right? All right. You guys are doing good. Okay, so let's go into more detail about flow acceleration, because it's acceleration that causes non-uniform flow. One kind of acceleration causes that, and a different type of acceleration causes unsteady flow. So let's break it down and differentiate between the two. Okay, so a particle that's going along a path line that may be curved, it's going to experience two components of acceleration. One component of acceleration is tangential, and that is related to its change in speed. Remember that velocity has two components. It has a magnitude and a direction. And so when you change the magnitude of velocity, then there would be a time-dependent tangential acceleration. On the other hand, since you can see this particle is going around a curved path, that means that its direction is going to be changing. Even if the magnitude of its velocity, even if its speed was constant, it would still be experiencing an acceleration having to do with its change in direction. And so here, this is a centripetal acceleration that's normal to the path line. And so it's depending on the particle's position. So let's look at a couple of video clips that illustrate some differences between those two different types. Okay, so we've just watched these video clips that are illustrating the change in acceleration with respect to time and position. And so if we're thinking about a particle's movement in three directions, then we'd need to keep track of its acceleration in each of those velocity components, x, y, and z, as well as its change in velocity with respect to time. Those are the options, that it can be changing in three directions and over time. So local acceleration occurs when flow is unsteady. Another way you could think about it is that local acceleration causes unsteady flow conditions. Because a particle is accelerating with respect to time, then that is the definition of unsteady flow. And so local acceleration, which is what most of you have learned about in, let's say, physics class. You know, the classical definition of acceleration is some change in velocity over time. So, you know, a rocket-propelled semi-truck, for instance. Now, convective acceleration is a little bit less familiar to most people, and it is the acceleration that's associated with non-uniform flow. So some sort of a change in velocity with respect to position. And so if you look at this nozzle that's pictured, what you can see is that the diameter of the nozzle is contracting. You start with a big diameter and a relatively slow fluid velocity, but then the fluid velocity has to increase as the diameter of the tube decreases. And the reason for that is that, remember, water and other liquids are incompressible. We can't, with some exceptions, you know, a lot of force will have a very small degree of compressibility, but it's such a minor amount of compressibility that we say that fluids are essentially incompressible. So what that means is if you put in 1 liter in the inflow side, then you're going to have 1 liter come out through the outflow side. And so the flow rate has to be the same, and the only way to make that happen when the cross-sectional area decreases is by increasing the outflow velocity. So in a flow field like this, where you have a low flow rate going in and a big flow rate coming out, there had to have been some acceleration there. And the acceleration is convective acceleration. It's change of velocity with respect to position. And if you look at the shape of the nozzle, this is just, of course, a conceptual drawing, but you can see that probably just in the opening of the nozzle, there's not much acceleration because those two walls, the pipe walls, are parallel to each other. But where is the fluid changing velocity the fastest? What you'd want to do is you'd want to see where are these pipe walls the least parallel. And that would tell you essentially where is the acceleration the greatest. And so if we had some sort of an equation that related how quickly the diameter is changing as a function of position, then that would enable us to find out what is the acceleration at every point in the flow field. Because the acceleration right here at the beginning is essentially 0. And at the end, there's no acceleration because, again, the pipe wall is parallel to the other side. But here in the middle, where the diameter is changing the quickest, there's going to be the most amount of acceleration. And so somewhere it's going from 10 to 20, and we'd want to calculate the acceleration because it's going to have an effect on pressure. That's kind of where this is all headed, like why we care so much about local and why we care so much about convective acceleration is we need to develop equations that predict pressure. What was our old equation? Back in Chapter 2 and Chapter 3, what formula did we use to predict changes in pressure? Change of height, gamma, right. So what was that equation called? Oh man, you guys flushed your memory right after the exam, huh? Hydrostatic, yeah, good. So hydrostatic equation was the first way that we had to predict changes in pressure. But the hydrostatic equation only works when conditions are static. So the reason why we're talking about acceleration is that the different types of acceleration give us a clue of how the pressure is going to change when the water is moving. And so local acceleration, which is associated with unsteady flow conditions, we're going to use that idea to give us one formula for predicting pressure change. And then we're going to use the idea of convective acceleration, which is associated with non-uniform flow, and we're going to turn that into another equation. So in the end, we'll have three equations. We'll have hydrostatic equation for predicting pressure change when the fluid's not moving. We'll have the Bernoulli equation, which we're going to use for predicting a pressure change when there's convective acceleration and non-uniform conditions. And then we're going to use Euler's equation to tell us how pressure changes when there's a local acceleration, meaning that conditions are unsteady. So that's kind of why we're talking about acceleration, just to give you the preview of what lies ahead. Now, remember that comparison table of the differences between uniform and non-uniform, steady versus unsteady. Last time you saw this slide, we just had the first bullet point where we were defining what those two terms mean. So non-uniform is when there's a change in velocity with respect to position. Steady is when there's no change in velocity. Unsteady is when there's a change in velocity with respect to time. So the key difference there, the word that's different, position versus time. Non-uniform versus unsteady. Okay, so now what we've added to our list here is the type of acceleration that's associated with each of these flow conditions. Convective acceleration is associated with non-uniform. Local acceleration is associated with unsteady. We'll continue to fill this in. Let's get more into the convective acceleration by looking at a specific example. And this is kind of a special example, and the reason why I say it's special is it's one of just a handful of times in the courses that I teach where we use calculus. You know, you go to all the trouble of learning calculus and taking differential equations, but the dirty little secret of civil engineering is that you don't actually use calculus all that much. Don't repeat that, though. That's the dirty little secret of civil engineering. But today we are. We are going to use calculus a little bit. We're going to use the chain rule, and you'll see why in just a moment. But let's look at this nozzle. What we know from this nozzle is that we have an initial velocity of 10 and a final velocity of 20. And in this example, we're provided a formula that describes the velocity as a change of position. So this formula says the velocity is the initial velocity divided by some factor that changes based on our position x, where you can see x is 0 at the nozzle's entrance, and then when x equals L, we're at the exit. So first of all, let's check this formula with the 2 points where we know the velocity to make sure it's working. So at x equals 0, what is the velocity going to be? It's going to be our initial velocity of 10 meters per second divided by 1 minus 0.5 times 0 divided by L. Okay, so if this second term here is 0, that just means it's 10 divided by 1. So it's 10 meters per second. So far the equation makes sense. Let's see at x equals L. So that means when we're at the end of the nozzle, at that position, from the sketch here, we can see it should be 20. So let's make sure that's true. U equals 10 meters per second divided by 1 minus 0.5 times L divided by L. So the L's cancel. That means we've got 1 minus 0.5. So that's 10 meters per second divided by 0.5. So it's going to be 20 meters per second. Okay, things are looking good so far. This formula, at least based on the 2 points that we know, seems like the velocity is being predicted fine. What we could also do is we could prepare a graph just to, if we want to see what does the change in velocity look like. And I did that before class. I couldn't resist opening up Excel. And here's our length. I guess in the problem statement here, it says that the length L is 0.5 meters. And what we're going to want to do in this example is find out how much acceleration is there halfway, like in the middle of the nozzle. And so if you look at what is the velocity as a function of position, it looks like in the middle of the nozzle, that's where the curve is pretty steep. Like that's where it's changing the most. And so there's going to be a fair amount of acceleration here at 0.25. So we've got on one axis the distance from the entrance, on the other axis the velocity. You don't necessarily need this figure to solve the example. I just thought it would be interesting to graph this function. Okay, so here's what we're going to do. This is what our approach. The definition of convective acceleration is a little bit different than the definition of local acceleration. Do you remember what local acceleration was? What's the formula for that? du dt, change in velocity over time. Now, what this is showing on this slide is that convective acceleration at any particular point is the velocity at that spot multiplied by du dx. So du dx is how much the velocity is changing at that spot with the respect to position. All right, so what we're going to do is we're going to use the chain rule to tell us what is du dx. So we are given, let me just for a moment turn the screen off so that I can bring the solution up on the screen. I'm going to solve it on the whiteboard. There we are. All right. So what do we know here? We know that L equals 0.50 meters. Our initial velocity is 10 meters per second. And we want to find out how much convective acceleration is there at the middle of the nozzle. So at 0.25 meters in. So the nozzle is choking down, and that's what's causing the velocity to exit at 20 meters per second, whereas it was entering at 10 meters per second. And the overall nozzle length is 0.50 meters. And we're going to find out here in the middle what is the convective acceleration A sub c. All right. So A sub c is the velocity at a spot multiplied by du dx. So the chain rule says that du dx is du dm multiplied by dm dx, where m is just some intermediate variable that we're going to use because we have in our velocity description, velocity is u naught divided by 1 minus 0.5 x divided by L. So what we're going to say is that we're going to have m be 1 minus 0.5 x divided by L. So we're just going to use this entire denominator and assign this the intermediate factor of m. So what that means is that we have u equals u naught divided by m. So this is our velocity function, where, of course, this is the definition of m. In other words, that's the same thing as saying we have u naught multiplied by m to the minus 1 power. So now we want to say du dx of this. So du dx equals d u naught to the m minus 1 power dm multiplied by dm, which is, again, 1 minus 0.5 x divided by L dx. Okay. So here we're just making the substitution of the u and the m. So, excuse me, that is, if we take the derivative of this first function with respect to m, that's minus 1 u naught m to the minus 2. And if we take the derivative of this other function with respect to x, then what we're left with is negative 0.5 divided by L. Okay. So remember what the definition of m is. So now, keeping that definition of m in mind, what we're going to do is substitute that back in. So du dx is going to be minus 1 u naught divided by 1 minus 0.5 x divided by L squared in the denominator. That's the same thing as m to the minus 2 power. It's just putting it back down in the denominator and squaring it. And that's multiplied by negative 0.5 divided by L. Okay. Okay, so that is 0.5, if we combine it all together, 0.5 u naught divided by L 1 minus 0.5 x divided by L, and all of that squared. So let's see. Just combined it together. The two negative signs cancel each other out. So once we combine the two terms, that negative sign is no longer in the equation. And then we've got L multiplied by 1 minus 0.5x divided by L squared. Okay? Any questions so far? Let's make some substitutions now. This is du dx. Oh, that's called the velocity gradient. Du dx is the velocity gradient. It's how the velocity is changing with respect to position. Let's keep in mind our definition of what is L and what is x. So if we want to know the convective acceleration, u du dx, then we have 0.5 u naught squared divided by 0.5, because now I'm substituting in the actual numerical value for L, so it's 0.5 meters. And so it's going to be inside the parentheses there, 0.5 times 0.25 meters, because that's the value for x, divided by L, which is 0.5 meters. And then I need to remember to square everything that's inside the parentheses there. Oh wait, did I miss something? Yeah, I needed to write the 1. Okay, 1 minus all of that. Okay, so here we've got 0.5 times the velocity, and looks like I failed to square it both times. Boy, oh, okay. Yeah, it's, so u du dx is just where it comes squared. So the velocity gradient was the velocity u naught to the 1 power. But then when I multiply u times du dx, that's when it is u naught squared. Okay. So what that works out to, if we substitute these and do the calculations, and so with your calculator you could see that 1 minus half times half is going to be 1 minus a quarter. So multiply that by 0.5. Then u du dx is u naught squared divided by 0.75 to the 3rd power. And remember that our definition of, this is the 3rd power. Our definition of velocity, when this got the 2nd power, then this became the 3rd power, because in the denominator of the velocity, down here we've got 1 minus 0.5x divided by L. Okay, so that's 0.75 to the 3rd power. So that works out to be 2.370 u naught squared. And so in the end, the velocity is going to be the velocity multiplied by this 2.370. If our initial incoming velocity is 10 meters per second, and square that, that's 100. So then that means it's going to be 237 meters squared per second is the convective acceleration. So here you can see that we substitute in the velocity, multiply it by 2.37, and at this location in the middle, the velocity is changing at a rate of 237 meters per second squared. And this is the thing that's sometimes confusing for people is convective acceleration is a change in velocity because of a change in position. But yet, it still has units that are related to time. So the units of convective acceleration are still meters per second squared, and that's the way it needs to be. But we arrive at those units by multiplying velocity by the velocity gradient. So if you think about, do those units work out, it's meters per second in velocity multiplied by meters per second and then meters. So we're going to end up with the meters down here canceling out one of the meters from the numerator, and then all that's left is 1 meters and 2 units of time in the denominator. So I mean, the units do follow from this being the equation for convective acceleration, but still it is a little bit unusual that we're thinking about this acceleration being related to position, but it still has units that are based in time. So you'll have a homework assignment where you have to deal with convective acceleration. And I've tried to emphasize a couple of times that this du dx, the phrase for that is the velocity gradient. I think in the homework problem, if I'm not mistaken, in one of the homework problems you've got, they just tell you the velocity gradient. So you actually don't have to go to the trouble of using the chain rule to find du dx on that particular problem, because they've told you the velocity gradient itself. So what you'd need to do is find the velocity at a certain point and multiply it by the given velocity gradient. Okay, so that's a taste of convective acceleration. Now remember, steady flow is where conditions change over time. Well, it's where they don't. It's where velocity is constant with respect to time. Uniform flow is where velocity is constant with respect to position. And so the local acceleration is where there's a change in that velocity over time, and it causes unsteady flow conditions. Convective causes non-uniform flow. Now, as I mentioned earlier, we use those different types of acceleration to give us formulas that predict pressure change. And in a future class period, we're going to talk about the application of convective acceleration to give us Bernoulli's equation. But for today, what we're going to look at is how local acceleration can be used to predict changes in pressure in a formula called Euler's equation. Remember, there's a 2x2 matrix of combinations of steady and unsteady, uniform and non-uniform. So steady flow is associated with conditions that are constant over time. Unsteady flow is where conditions are changing over time. But uniform means that the flow velocity is not going to change as position varies, because the pipe diameter is constant. On the other hand, non-uniform flow would be where as the particles move from left to right, their velocity is going to increase because of their position, but you can have non-uniform unsteady flow. So what would cause non-uniform unsteady flow would be some sort of an apparatus that's shaping the flow field, like a nozzle, coupled with a valve that is opening or closing over time, so that the flow rate that's coming in, is varying. So you can have combinations, any variety of combinations of steady versus unsteady, uniform versus non-uniform. So what the Euler's equation is used to predict is conditions where you have where you've got the conditions are changing over time. And so it's going to be unsteady conditions, but you can only apply Euler's equation for uniform flow. Euler's equation wouldn't be able to handle something that is experiencing both unsteady and uniform at the same time. So Euler's equation is for local acceleration, and It models what happens when the fluid is accelerated. The hydrostatic equation is what we use to define pressure changes due to just going down through depth. And the hydrostatic equation already has an acceleration built into it. The hydrostatic equation has built into it the idea of gravitational acceleration. Euler's equation is what we can apply when there's any other acceleration besides gravitational. In fact, it incorporates gravitational acceleration into the Euler's. It's got both. So this particular tank, if you wanted to have a prediction of the pressure at a certain depth, then the equation that you'd use is, if it's hydrostatic conditions, you'd use the hydrostatic equation, which is that the delta P is delta H times gamma. Well, we can expand that out with the definition of gamma. And remember that gamma is the density of a fluid multiplied by g, where g is gravitational acceleration. So a hydrostatic equation was assuming that there's just gravitational acceleration. But in this case, this is posing the question of what if you had a situation where the tank itself was accelerating upward. So not only is there going to be the gravitational effect, but there's also going to be the effect of its upward acceleration. So what you do in that case is, just to give you an idea of, Euler's equation takes into account gravitational. If we had a change in pressure that we wanted to predict because it's accelerating upward, you should kind of instinctively know that the pressure changes are going to be greater than it ordinarily would under circumstances where it's just steady. Like if you accelerate it up, then kind of think about what happens to you when you're accelerated forward. Let's say you're sitting in a really fast car. If you're accelerating forward, the pressure accumulates on your back. That's where you feel it. So the pressure increases in the opposite direction of the acceleration. Let me write that down because this is important. The pressure increase is in the opposite direction of acceleration. So the way to remember that rule is if you're accelerating forward, the pressure increase is backwards. So you feel the pressure on your back, not on your front. So in the case of a tank, if we're accelerating it upwards at 9.81 meters per second squared, then what we'd need to do is we'd need to have the g that we're going to put into here, the acceleration term, would actually be 9.81 meters per second squared plus another 9.81 meters per second squared. So if we were going to look at the pressure at a depth of 1 meter as the tank's accelerating upwards, delta H is still 1 meter, and the density of this, being water, is still 1,000 kilograms per cubic meter. But now for G, we would say 9.81 meters per second squared plus 9.81 meters per second squared. So the pressure change is going to be 19,620 newtons per meter squared. That's if the tank is accelerating upwards. What if it was accelerating downwards at G? How would pressure change then? Yeah, instead of adding the two together, then what we'd do is we'd find the difference. If it's accelerating downward at 9.81 meters per second squared, then actually there would be no pressure change in the liquid. So if you throw a water bottle out of an airplane and it's falling downward, there's no pressure change in the liquid as long as it's accelerating at g. Now, it's going to reach the terminal velocity because of wind resistance, but let's say that a bottle of water was accelerating downward inside of a vacuum, And the vacuum is what's going to make that there's no wind resistance. So it actually would accelerate downward at 9.81 meters per second squared. In a situation like that, where there's essentially no gravity, like in space, if they have those water bubbles that just kind of float around and the astronauts drink out of them and that sort of thing, there's no pressure change as you go side to side, up and down. There's no pressure change in that liquid because there's no acceleration. Okay. So this is just kind of a special case where what we do if we have the tank accelerating upward is we would add gravitational and the additional acceleration that it is experiencing. Any questions about this first illustration? This isn't Euler's equation, though. This is just kind of a preview of one of the factors that Euler's equation is taking into account. And so what we did is we said, let's expand out this definition of gamma that's in the hydrostatic equation to specifically identify the acceleration term. And instead of using just g, let's combine all of the accelerations together. But this approach really only works when the acceleration of the object is vertical. There are other cases where it's not vertical, where we have to use a more complete equation that can handle everything. And so what we're going to do to get that equation is keep in mind that the sum of imbalanced forces on a particle of certain mass cause that particle to accelerate. So just like the rocket sled that was testing the ejection seat, the reason why it accelerated was because there were more forces on the back where the rocket was spewing out gases than on the front. And so that's why it accelerated. So consider a particle that's experiencing that acceleration. This is showing kind of like an element of water where the reason why it's oriented the way it is, this direction, is just to illustrate the fact that Euler's equation is able to predict a change in pressure regardless of whether the acceleration is vertical or horizontal or at some inclined direction. So let's just look at a few things that are on this sketch. What it's saying is that you can first of all look at the directions. We have the x, y, and z directions. And so the orientation of this acceleration that the particle is experiencing, the delta L direction, looks like it has some component in the x and some component in the z. And so there's going to be a change in pressure on the back face of this compared to on the front face of it because it's experiencing acceleration in the L direction. You can see here at the center of the object, they're saying that this control volume of water is accelerating in the L direction. And of course, there is a weight of the water acting downward, which is associated with the volume of however much water there is. But in the L direction, the particle is accelerating, and because of that, there's going to be a difference in pressure between the front face and the back face, partly because of the acceleration it's experiencing, and also partly because of the gravitational effect. So what we'd need to do to solve a problem like this is find out what is the mass that we're talking about, and based on the acceleration that it's experiencing, then we'll be able to calculate the change in pressure. And the directionality of the change in pressure is related to this statement, that the pressure increases in the opposite direction of acceleration. So if it's accelerating in the L direction, you can see here the acceleration vector is in the L direction. That means that the pressure would be greater on the bottom side of this cylinder than on the front side of the cylinder. And then gravitational effects are going to compound that even further. Okay, so just for a moment, I want to jump in with a little bit of information about problem 39 from your homework. In the problem, they say that there's like a piston that is connected to a container of water, and the diameter of the container is 1 foot. The depth of water inside of the piston is 10 feet. And they measured the pressure down at the bottom of the piston, and the pressure is 8 psig. Who can interpret what psig means? PSI probably everybody knows, right? What's that? Pounds per square inch, right? And what about G? Gauge. Okay, so what that means is that compared to the pressure of the air that's above the piston, the pressure down at the bottom of the piston is 8 pounds per square inch higher. We're going to need to convert that to pounds per square foot. But the dimensions say that we're at a depth of 10 feet. The pressure is 8 psi-g, and then they want to know what's the acceleration that's causing that pressure. Like how quickly upward is the piston accelerating. So a couple of hints on how to solve this. First of all, remember that to convert from psi to psf, what you have to do is multiply by 144, because there is 144 pounds per square, 144 pounds per square foot. Yeah, 1 pound per square inch is 144 pounds per square foot, because if you have 12 inches by 12 inches, and in each one of these inch square elements we have a pound, then in 1 foot by 1 foot, then there's going to be 144 of the pounds. So you're given the pounds per square inch. You're going to need to convert that into pounds per square foot. Now, of course, if you're working in traditional units, G isn't 9.81 and density isn't 1,000. Density in the traditional units is 1.94 slugs per cubic foot. And when you multiply a slug by an acceleration of 1 foot per second squared, then you'll get 1 pound of force. So the way that you can solve this one is by applying that vertical acceleration pressure change formula. So in the previous slide, we said that if there's some elevation difference, 10 feet, multiplied by some density, 1.94 slugs per cubic foot, then the pressure change that you observe is due to the accelerations. So what you need to do is ask yourself, is the pressure down here at the bottom higher or lower than it would have been if conditions were static? And if it's higher than conditions would have been when pressure was when it was static, that means it's accelerating up. If the pressure down here at the bottom is less than it ordinarily would have been, that means it's accelerating downward. So compare 8 psi to just what the hydrostatic equation says the pressure should be, 10 feet down. And so if I remember correctly, the pressure is higher than it ordinarily would have been at a depth of 10 feet. And so in that case, then, the sum of the accelerations is what you're going to be solving for. You know one component of that sum. It's the gravitational component. But then the difference between gravity and that sum of a sub z that you'll solve for is how much it's accelerating, the piston itself. So there, again, are two different components of a sub z. A sub z includes g plus the actual physical acceleration of the piston. Okay, now Euler's equation. Let's get into it. We've got this formula for Euler's equation, and what it says is that the piezometric pressure changes in the L direction. The minus sign says that it changes with the opposite direction than the acceleration in the L. So if there is a positive increase in acceleration in the L direction, if you're accelerating in one direction, then the pressure is increasing in the opposite direction. Now, this is the version of the Euler's equation that will be on any formula sheet that I give you for exams. But you have to make some changes before you can actually start plugging numbers into it. And so I always try and do my best to warn you about the common mistakes that sometimes people make. And I'd say one of the common mistakes on Euler's equation is that people just start substituting numbers into this. But you can't. You have to transform Euler's equation a little bit depending on what direction the acceleration occurs. So let's say that the acceleration is happening horizontally. in the x direction. So the way that you translate this formula into an acceleration in the x direction is shown. And it assumes a linear variation in pressure in the direction of acceleration. And so what it says is that the change in piezometric pressure over some distance, delta x, is going to be affected by the acceleration in that direction multiplied by the density of the fluid. We can rearrange this a little bit further to solve problems of the sort you're going to see, because the way that you apply Euler's equation is between 2 points. There will be one spot where you know the pressure and another spot where you don't, and you'll need to find out what is the pressure at that other location. Or, like the example that you just saw on the previous slide, maybe you know both of the pressures and you're trying to solve for the acceleration. Euler's equation can do that too. So in the example we just saw, if you wanted to do like the full-fledged version of Euler's equation, what we had was we were acting in the z direction, and location 2 versus location 1, we knew that the pressure up here, P2 is 0, and down here P1 was it 8 psi? 8 psi G. So what you could do is solve for the acceleration in the x direction by substituting in, we're talking about z. You can also rearrange Euler's equation in the z direction. Just every place it says x, you would put in z. So if the acceleration is vertical, then delta x would be delta z instead. Euler's equation is going to be solving between 2 points. And the convention for what location is 1 and what location is 2 is an important part of Euler's equation. And previously it didn't matter. When you were doing the hydrostatic equation, remember, sometimes we'd say we want to use the hydrostatic equation between a pair of points, and we could just pick 1 and 2 and it could be interchangeable. And we'd say P1 divided by gamma plus Z1 is equal to P2 divided by gamma plus Z2. And it didn't matter if we said 1 versus 2 is here, or we could have said 2 versus 1. There was really no rhyme or reason. There was no right answer or wrong answer for assigning which location is 1 and which location is 2 with the hydrostatic equation. But when we use Euler's equation, there are rules. And the rule is that location 2 is the spot that is furthest to the right if you're working horizontally. So there's going to be some direction that we say is positive x. And so this is our positive x direction. Up is our positive z direction. And so if you have 2 points and you're trying to find the pressure change between them, then number 2 is the one that's furthest to the right. Or if you're working vertically, number 2 is the spot that's highest. And so in that accelerating piston problem that you've got, location 2 is the higher of the two, the one with the most z. And so that's why I labeled the 2 as the pressure at the surface and 1 is the unknown pressure down below. It has to do with this convention. So just to emphasize, in the x direction, 2 is further to the right. In the z direction, 2 is further above, more elevation. Okay, let's work an example, because that's, I think, what can sometimes make it a lot easier to understand. Let's say that we had a truck that was hauling gasoline. And since it's gasoline, you can see that there's some different unit weight that's provided there. It's different from water. And so let's find the density of this fluid given the unit weight of gasoline. So density is gamma divided by G. And we're told that this gamma is 6,600 newtons per meter cubed. And of course, we know that G is 9.81 meters per second squared. So this fluid, the gasoline that's in the tank, is 672.8 kilograms per cubic meter. And it's slowing down at a rate of 3.05 meters per second squared. So what that means is that the acceleration in the x direction is minus 3.05 meters per second squared, because it's slowing down. So it's already moving to the right, but its acceleration is to the left because it's slowing down. So that's why I use the negative sign. You can see from the sketch we've got some dimensions here. The tank is 6.1 meters in width, and the tank depth is 1.83 meters. And I guess this tank must be vented to the atmosphere, which seems like a bad idea for gasoline, but the tank is vented to the atmosphere just so that we can say we know the pressure at location T. So here at location T, we've got a known pressure of 0. Okay? So we want to know what's the pressure over at location A, and then we'll try and figure out where is the pressure the greatest and what is the pressure at that spot. So let's just think, first of all, before we start plugging numbers into the formula, let's think qualitatively. The pressure at A, is it going to be bigger than the pressure at T or less, based on how the truck is decelerating? What was that written rule? The written rule was pressure increases in the opposite direction of acceleration. So the acceleration here is backwards, since the truck is slowing down. What that means is the pressure will increase in the opposite direction. So if the truck is accelerating to the left, then the pressure will increase to the right. So what we should see once we start doing the calculations, PA should be greater than PT. So if we plug the numbers in and we don't see that, that tells us probably we've got an error someplace. Maybe we need to reconsider what we've got. Okay, so starting with Euler's equation, let me just transfer this sketch up onto the board. We've got essentially a tank that is 6.1 meters in width and 1.83 meters in height. We know the pressure here is 0. We already calculated the gamma. We're going to find out what is the pressure here at A. And this is what we're calling location B. All right, so part 1, find P sub A. We want to find out how much is the pressure at A. It's accelerating to the left, so we know that the pressure should be bigger than location T. Starting with Euler's equation is negative the delta L, P plus gamma Z is equal to density acceleration in the L direction. Now, our acceleration is in the x direction. So for acceleration L equals acceleration in the x direction, then the way that we're going to translate this is negative delta divided by delta x, pressure plus gamma Z is equal to density acceleration in x. Now, A is location 2, and T is location 1. So this was location T, the one on the left. The one on the right is A. And remember, the convention is that whatever has the most x, where our x direction is increasing in the right, whatever has the most x is going to be labeled location 2. Whatever has the least x is labeled location 1. And so we've labeled those. And so that's going to have us say the pressure plus gamma Z at location 2 minus the pressure plus gamma Z at location 1 is equal to, that's the delta part of it. So the delta of the piezometric pressure. And then we moved over to the other side of the equation, the negative delta x multiplied by the density multiplied by the acceleration in x. So now let's substitute in A and T. What this translates to is the pressure at A plus gamma ZA minus the pressure at location T plus, actually minus, since we distribute that negative sign to both terms, to the pressure and to the gamma Z term. So minus pressure at T minus gamma ZT is equal to negative delta x times density times acceleration in x. Okay. The thing that makes this problem a little bit simple is that both A and T are at the same elevation. And so this term gamma ZA and minus gamma ZT, well, ZA equals ZT. The elevation above some datum, like it doesn't matter where we use as our elevation datum. If we use the bottom of the tank, let's see, this is our Z datum, then what it means is that the elevation of location T above that datum is the same as the elevation of location A. So we can cancel out this gamma ZA term. We can cancel out the gamma ZT term because they're equal. And let's solve for P sub A. P sub A is going to be P sub T, because we move that over to the right-hand side of the equation, minus delta x times density times the acceleration in x. Okay, so if we substitute in the given values now, the pressure at T is 0 minus delta x. So how far apart are they in the horizontal direction? It's 6.1 meters. The density that we calculated at the beginning is 672.8 kilograms per cubic meter. And then the acceleration in the x direction, we have to be sure that we write the negative sign there. That's a critical part of it, is honoring our sign convention. So minus 3.05 meters per second squared. So let's calculate that. If you've got your calculator handy. (6.1) 672.8 3.05. So pressure at A is 12,517 pascals. Anybody else get that same value? Okay, good. Does it match what we expected? Like, we know that pressure should increase in the opposite direction of acceleration. So it's accelerating to the left. Pressure did increase in the right. So we said at the beginning that our sanity check was going to be PA is greater than PT, and it is. PA is greater than that value of 0 at location T. One way to think, go ahead.
So if the Z values were different, like there was a change in height,
Mm-hmm.
would you consider one to be like 0, and then as you're going down, would the difference between them be the height of the second one? Or would you just put in their respective heights in relation to some other point?
So you're wondering about 1 versus 2 when the which to use as 1 and which to use as 2?
More or less, yeah.
Okay, that's a great question, because the next part of this example asks you to find the pressure at essentially the bottom right part of the tank. And so let's look at that sketch again. All right, so his question was about, let's say that they're not at the same elevation, the 2 points in question. What if one of the points is high and one of the points is low? Which to call number 2 and which to call number 1 only depends on the acceleration direction. And so this is accelerating horizontally. So what we're going to do for the next step is we're going to compare the pressure at T, and we want to find out what's the pressure at B. B is going to be location 2. Even though it's lower, it doesn't matter that it's lower. What matters is that it's further to the right, because our acceleration is horizontally. So does that answer the question that you had? Okay. Are there other questions about this one? Okay, so for part 2, I'm not going to do it on the whiteboard. I'm going to pause for a moment and give you a chance to apply Euler's equation between T and B. You're going to use the same formula. This formula will be the same, but the z's aren't going to cancel out in the same way that they did before, because z1 is going to be different from z2. Their horizontal distance will still be the same. They're still going to be spaced horizontally 6.1 meters apart. The fluid density won't change. The acceleration in x is still the same. What will change is that, of course, we're solving for a different location 2. Instead of it being A, you're going to be solving for the pressure at location B. All right, so let me pause for a moment, give you some time to basically follow the same process to find out what is the pressure at B. And you're going where location 1 is T and location 2 is B. Even though it's accelerating to the left, still location 2 has to be the one that's furthest to the right. You know, if the acceleration is in the horizontal plane, then the rule is what we're going to label as location 2 is whatever has the most x. You know, whatever has the most position in the direction of your assumed positive coordinate system. So what that means is that we have to have, when we're setting up Euler's equation, it's going to be PB plus gamma ZB. And you can see I've crossed out ZB, and the reason for that is I assumed that the elevation, let's measure elevation relative to the bottom of the tank. And so the elevation of location B is 0. But the elevation of location T is 1.83 meters above the datum. So I assigned the elevation variables here and rearrange the equation in terms of the pressure at B. So then the pressure at location T is going to be the pressure that we had above it. You know, in the previous step, we found that the pressure at A was 12,517. So here's that 12,517, and that was because of the horizontal distance between them. But then this other term is taking into account that location B is below location A. And so it's taking the hydrostatic effect into account as well as the acceleration, the horizontal acceleration that's occurring. So Euler's equation is nice. It will take the elevation difference between 2 points into account as well as whatever acceleration, whatever additional acceleration beyond gravitational is occurring. So the hydrostatic equation is built into Euler's equation, in other words. It's built in, and then there's going to be some additional acceleration beyond gravity that you have to identify, and then Euler's equation will tell you the effect of that as well. So the question asked, where's the pressure going to be the greatest? And just by inspection, we can see that the pressure is going to be greatest down here at the bottom and furthest to the right. Because the further to the right we go, the more the pressure increases, since that's in the opposite direction of the acceleration. And the deeper down you go, the pressure increases. And so location B was the furthest to the right and the lowest down. All right, that's it for today. I will see you on Tuesday. Hi, Corey. Oh, not much. You just got perfect timing. I just finished my class. Yeah.